Hi guys, you're welcome to Grad Academy. So in this Algebra tutorials, I'll be taking you through problems and how you are going to solve them. Okay, so I'll write the problem, I take you through how to solve them for you to get the full understanding and also for you to prepare for your exams. Yeah, so let's get straight into the video. The first one I'm going to touch on, I'm going to start from the beginning, then I'll move down. So I'm starting from mathematical induction, okay? So I have a problem which I'll write. So we quickly go through different problems as much as possible. So I have 1 squared plus 2 squared plus 3 squared plus 3 dots plus n squared is equal to the expression n multiplying n plus 1 multiplying 2n plus 1 all over 6, right? So when we talk about mathematical induction, let me explain it before we proceed. Mathematical induction is simply trying to test that a relationship, mathematical relationship, is true for all natural numbers, okay? So here you can see that they are saying that 1 squared plus 2 squared plus 3 squared plus infinity, or so far as it's following the same pattern, will always give us the expression the n multiplying n plus 1 multiplying 2n plus 1, right? Yeah, so once you have this, then the next thing we are going to do is we have some steps for you to follow for us to make that proof, okay? So let's move straight to how to solve a mathematical induction. Assuming you've seen this in the exams, how do you solve this problem? Simply write your solution and we move to the first step. The first step is what we call the base case, okay? So in the base case, what we are going to do is you are going to test for the least number. So here we are saying that this is a series. Please take note. It's a sum of a sequence, okay? I have 1 squared, 2 squared, 3 squared, meaning the next one will be what? 4 squared, 5 squared, so nth 10. We don't know, right? And what the rule is saying is that no matter the number of tens you are going to add, it will always give us this expression, where n means the number of tens you are. So if you add up to the sixth 10, you put 6 here and it will always give you the same answer. So that is what we want to prove, whether this is true for all natural numbers, okay? So for the base case, let's test for n equals 1, okay? So testing for n is equal to 1. On my left side, what is my first term? Remember, many people make this mistake. On the left side, what they do is they come and put 1 into n squared. Please, it's wrong. We don't do that, okay? It's wrong. You can do that, it's true. Let's say for some number of terms it's true, but it can fail you in some. For this particular expression, you see it clearly. When you put 1 here, it will work. When you put 2 here, it will work, right? But not every problem. So take note of that. Whenever we say for n equals 1, we mean our first term. So this is first, second, third, fourth, fifth, until we reach the nth term. So if you want to prove for your base case for n equals 1, you mean the first term. Take note. It may work for some problems, but not all, lest you be in trouble. So you are looking at the 1 squared, okay? So once you have this, then the next thing you are doing is we are going straight to putting. So here's 1 squared. So I'll just select 1 squared, right? It's equal to, on the right side, I simply put 1 wherever I see n, right? 1 plus 1 multiplying 2 multiplying 1 plus 1 all over 6. Therefore, I'll get 1 on my left side. On my right side, I'll get, this is 2, right? 2. So I have 2 multiplying, this is 2, 1, 2 plus 1, 3 all over 6. And this is the same as 1 is equal to 1. This is 6, it will cancel, right? As simple as that. So we just say that our base case is true, as simple as that. So once we know that our base case is true, 1 is equal to 1, we move straight to the induction hypothesis. Induction hypothesis, okay? For the induction hypothesis, what you are trying to do is you are going to assume, okay? So we will assume for n equals k, that is an unknown term. We can do for second, third, fourth, fifth. So what about if we can do for an unknown term, right? That is the concept of induction hypothesis. We will assume that our statement is true for an unknown term, and if that is true, then it should be true for the next term after that unknown term. That is the concept of mathematical induction. So at the induction hypothesis, it's very simple. You just write proving that, assuming, it's an assumption, okay? You don't prove here. Here is an assumption. So the induction hypothesis is an assumption. So he said, assuming the statement is true, okay, assuming the statement is true for n is equal to k, an unknown, okay, n equals k. So in our induction hypothesis, we say that 1 squared plus 2 squared plus 3 squared plus now here is k, okay, is the kth term. So remember, k squared is equal to, wherever you see n, you put k multiplying k plus 1 multiplying 2k plus 1 all over 6, okay. So once you have this, we say that this statement is true. So this statement that we have here is true from our induction hypothesis. Wherever you see this, it holds because we have assumed that it's true. Yeah, so that's what the induction hypothesis does. Then the next thing we do is we move to the inductive step. That is where the main proving comes in, the inductive step. So what do we do? So here we prove for n is equal to k plus 1, okay. So proving for n equals k plus 1, proving for n is equal to k, proving for n equals k plus 1. Now we've already assumed that our statement is true for k. For our statement to be true for every natural number, then it means that the number after k should also work. So let's see. At this point, you simply write 1 squared plus 2 squared plus 3 squared plus k squared, right? Now we are looking for when the number after k is correct. So here you also write plus k plus 1 all squared. But the number after k is k plus 1. So our k plus 1 term. So that is why we bring k squared then plus k plus 1. Please don't be tempted to remove k squared and put k plus 1 squared there. You make an error. That is the common errors students do make, okay. So this should be equal to, whenever you see k, you put k plus 1, right? So k plus 1, I'll have k plus 1 plus 1. Take note for this side. Then this side I'll have 2 multiplying k plus 1, right, plus 1 all over 6. The goal now here is to make sure that our left hand side is equal to our right hand side, as simple as that. So on my left hand side, you can see that from this side to this side is the same as what we have here, okay. Our hypothesis is saying that whenever you have 1 squared to this end, it's always equal to this. We have assumed that that is true. We move straight to it and make substitution that this is equal to this and is true. So this is the use of induction hypothesis. It's helped her to get a substitution in the inductive step. So here I'm going to replace this with k multiplying k plus 1, 2k plus 1 all over 6, right, plus k plus 1 all squared is equal to what I have here. That will be k plus 1 in one bracket. This gives me k plus 2, right? Then this gives me 2k plus 2 plus 1. So 2k, then this is plus 2, right? 2 times 1 is 2, then plus 1 plus 3. As simple as that. All over 6. So our goal here is to make sure that our left hand side is equal to our right hand side, okay. So at this point, what do? We simply simplify what I have here. I simplify what I have here, or I can choose to make one equal to the other. The goal is they should be the same, okay. So how do I do this? This is a simple algebraic expression. I'll have k multiplying k plus 1 multiplying 2k plus 1. So now let me divide it into my left hand side and my right hand side, okay. So let me do it this way. So I have my LHS, my left hand side. Let me do it this way. So I have k multiplying k plus 1 multiplying 2k plus 1 all over 6, right, plus k plus 1 all squared. So simply I'll cross multiply, as simple as that. So this becomes k plus 1. This is here, so I'll have k plus 1, k is out, multiplying 2k plus 1, 6 multiply, so plus 6 multiplying, here you have to expand, so it's the same as k squared plus 2k plus 1, right, all over 6. Now we get, now here you get k squared, right, I'm multiplying this, k squared plus k, right, in one bracket, 2k plus 1. Then here I'm going to get 6k squared plus 12k, right, plus 6. All this over what? 6. Okay, so that's my left hand side. So So on my left hand side, I'm going to have here, I'm still multiplying this, k squared times 2k, that is 2k cubed, right? Then k squared, I multiply 2k by k squared, I got this. 2k by k will give me 2k squared, right? Then 1 plus this, I'll get k squared. 1 plus k times k, I'll get plus k, plus 6k squared plus 12k plus 6 all over 6, right? So now you can see that I have only 1k cube. So 2k cube is on one side. I have 2k squared, 3k squared, right? Plus 6k squared, that is 9k squared. I have k plus 13k, then plus 6 all over 6. Now let's come to our right hand side. Our right hand side, we have 3 brackets, we have to multiply, okay? So on my RHS, what do? I'll multiply this. K will multiply k, I'll get k squared, plus k will multiply 2k, plus 1 will multiply k, I'll get k, plus 1 will multiply 2, I'll get 2, right? All this expression will multiply 2k plus 3 all over 6, right? So this moves forward, and my first expression, I'll end up getting k squared plus 3k plus 2, multiplying 2k plus 3 all over 6, right? Now let me finally expand this. 2k is multiplying everything here, okay? So let's observe closely. 2k times k squared, I'm going to have 2k cubed plus 2k times this, 6k squared, right? 2k plus 2 times 2 is plus 4k. Then plus 3 times k squared is 3k squared. 3k squared plus 9k plus 6 all over 6, right? This gives me 2k cubed out. I have 6k, I have 3k plus 9k squared, right? 4k plus 9k, that is 13k plus 6 all over 6. Now let's compare. So looking at what you have here on our left hand side and what we have here on our right hand side, you can equally see that this and this are what? They are equal. Therefore, our statement is true for all positive natural or all positive real numbers, or what to say, all natural numbers, okay, for n. Thank you for this question, and this is how you solve this type of mathematical induction. Now let's quickly solve another problem here. So let me clean from the app. Yeah, so let me write our second question. Please watch closely and try solving it on your own as well. You can pause it anytime and you solve it as well and compare that whether you are going to get your computations right. Okay, so our second question, let's solve one more mathematical induction problem, then we proceed. So let me say question 2. Question 2, I'm having 2 to the power n is less than n factorial where n is greater than or equal to 4. So now you can clearly see that this is an inequality and a factorial problem altogether. That makes it interesting, okay? So you have to prove that whenever you have an expression 2 to the power n, it is always less than this n factorial. Is this true? How do you prove this? You have to prove for every n. So as I said, we start with the base case, okay? So our solution for the base case, we test 4. Now they are saying that n is greater than or equal to 4. Please note this condition. Whenever they give you a mathematical induction, don't be in a rush to test for base case with n equals 1, because it doesn't always work that way. Depending on the condition, this is a mathematical statement, but the statement doesn't come alone. The person who made this statement said that it works provided that n is greater than or equal to 4. Okay, so then we move straight. How do you do this? So you say that for our base case, you can test for 4, 5, 6, 7, anything beyond 4, right? So testing for n equals 4, what do I get? On my left side, I'll have 2 to the power 4 less than 4 factorial. What is 2 to the power 4? Is 16. What is 4 factorial? 4 factorial is 24, right? So this is the same as 4 times 3 times 2 times 1. 4 times 12 times 2, 24. 16 is less than 24. Therefore, our statement is true and our base case is true. But our statement is not true for all natural numbers. We have to prove it first. Now let's go to induction hypothesis. For the induction hypothesis, you say that assuming assuming the statement is true for n is equal to k. Okay, for n equals k, we say that statement is true. Therefore, we say that 2 to the power k is less than k factorial, where k is greater than or equal to 4. And we are saying that this statement is true. This statement is true. So this is our induction hypothesis, and then we move straight to our inductive step. Our inductive step. So with our inductive step, what do we do? Proving for n is equal to k plus 1. That is the next term after k. Okay, so how do we do this? Wherever we see k, we put k plus 1 here on our left side. 2 to the power k plus 1 should be less than k plus 1 into bracket factorial. Okay, so how do I solve this? To solve this, always please take note, whenever they give you an induction, when you reach the inductive step, you surely use your inductive hypothesis. You can't solve inductive step without using the hypothesis. Please, you get it wrong because you are dealing with unknowns. Okay, so for us to get this question solved, then it means that we are working with the inductive hypothesis. Remember, 2 to the power k plus 1 by indices is the same as 2 multiplying 2 to the power k, right? It's less than k plus 1 factorial. Now, whenever you want to simplify mathematical induction involving inequalities and your factorial, this is what to do. Please, there is no formula for mathematical induction. In mathematical induction, you have to prove to the little 6-year-old child that what you have on your left here is less than what you have on your right, to say that the statement is true for all real numbers. How do we prove clearly that what you have on our left side is less than what you have on our right side? Okay, how do we prove it? Now, we can prove it only by simplification. Let's go to our base case. You realize our base case is saying that 2 to the power k, right, is less than what? What do you have here? When you have k factorial, we can say that k multiplying k minus 1 multiplying k minus 2, and it will go like that. Okay, now let's see something. So we are going to refer from here to simplify what you have here. Please take note of this step. So we are going to do this. So from the induction hypothesis, we can say that our 2 to the power k that we have here is less than k multiplying what? K minus 1. It keeps on deducting. That is why when you had 4 factorial, it became 4 times 3 times 2 times 1. So here we say k minus what? 2. Then our goal is this statement you have here is true. We have all accepted that is true. So this is our reference point. Whatever happens here is true. Now, how do we then compare this? This is 2 times this. So we can multiply our induction hypothesis by 2. Okay, so I'll have 2 multiplying 2 to the power k less than 2 multiplying the expression k multiplying the expression k minus what? 1 multiplying the expression k minus 1 multiplying the expression k minus 2. Okay, so you can clearly see this, right? So here we have 2 multiplying 2 to the power k, and that is exactly what you have in the inductive step. And we are saying that this 2 multiplying 2 to the power k is always less than 2k times k minus 1 times k minus 2, and that is true. So then we cannot even stand anywhere and say that if this one is less than this, then it means that this is less than that. It's never true. You have to solve and prove that this here we have here will be less than this. Already we know that this, our 2 multiplying 2 to the power k, is less than this expression. Our goal is simple. What should we do? We have to show that indeed our k plus 1 factorial here will also be smaller than this. That is all. Okay, so now let's see something here. So let's see. So here you can further in our inductive step. Please take notes. I'm still at the inductive step. Okay, so still at the inductive step, 2 multiplying 2 to the power k, right, is going to be less than k plus 1 multiplying this expression minus 1 will give me k. Then the next step will be what? K minus 1. Take notes, right? So you have this expression down. So I can, since I have k minus 1 here, you know, I could have added k minus 3, k minus 4, k minus 5. Okay, so I think it's going to be advisable to remain at k minus 1 so that the endpoint should be equal for comparison's sake. So my induction hypothesis will be 2 multiplying 2 to the power k is less than what? 2k multiplying what? K minus 1. So if this is less than this, will this be less than this as well? Well, let's see. You have k minus 1 here. You clearly see you have k minus 1 here. So it's equal. We have k here. We have k here. It's true. Now the only difference is 2. We have 2 here. We have k plus 1. Is 2 and k plus 1, which one is bigger? That's the question you ask yourself. 2 here and k plus 1, which one is bigger? Can we say that 2k is bigger than this, or that kind of thing, right? So the question then becomes like, we can see k minus 1. So k minus 1 is sorted. Our k is also sorted. So now you are comparing 2 and you are comparing what? K plus 1. But please take note. Remember, our condition that we have here is saying that k only works when k is what? Is greater than what? Or equal to 4. So if k is greater than or equal to 4, meaning that k itself cannot be less than 4. So obviously k is bigger than 2. I don't know if you get it. K is bigger than what? 2. I'm comparing this whole expression here with this expression to see which one is bigger. Then I'll make our conclusion. We see that there is k minus 1, there is k minus 1. It's ticked. They are equal. There is k, they are equal. The difference that can help us see the bigger one is the 2 and the what? K plus 1. That is what we are comparing here. And I'm saying that for you to make your comparison very clean, you can see that k from the condition says k is bigger than what? 4 or equal to 4. And you are telling me that 2 and k plus 1, which one is bigger? Yes, because it's k plus 1. The k itself alone is bigger than 4 or equal to 4. So meaning this expression here is bigger than 2. Therefore, I can say that I can confidently see that k plus 1 multiplying k minus 1 is bigger than what? 2k multiplying k minus 1. As simple as that. Then if this is bigger than this, then obviously this one will be less than this, because 2 multiplying 2 to the power k from our induction step is less than this expression. It is smaller than this. And if you realize that this one is bigger than this, then it means 2 multiplying 2 to the power k will indeed be smaller than this. And that is how you prove for inequalities. Yeah, that is all I have for you in this video. That's all I have for you for this particular question. Let's move to our next question quickly. So for our next question, we are moving straight to complex numbers. We are doing overall revision. So revision, we are solving different problems to touch different topics. So please take your notes and start solving along. Make sure that you understand every part, and don't forget to write in the comment section any problem, anything that needs to be addressed immediately. So the third question. Now find the value for this expression. You have I to the power 2 plus I cube over I to the power 4, all this expression squared. How do we simplify this expression? It's a complex problem, right? Now the complex, this squared, please. So how do we solve this? To solve this expression, we are going to rely on the complex operator I. Remember that complex numbers stem from the fact that -1 is equal to what? And we didn't have any value for -1, right? So for the square root of -1, because of that, when you square -1, you get what? Sorry, let me make it this way. So what I'm trying to say is, when we say square root of -1, you cannot solve it. That is why we choose a complex operator I to represent this expression. Therefore, if I square both sides, what do I get? I'm going to get -1 is equal to what? I squared. Meaning, anywhere you see I squared is what? -1. As simple as that. A -1. Now, look at our expression here. I have I squared here, meaning that is -1. Done. Plus, what expression we have here? I cube over I to the power 4. Now, by indices, this becomes what? I to the power 3 minus what? 4, right? Then I'm going to get all this squared from the question. So you will get -1, then this becomes what? Plus I to the power -1, all squared. What do you have here? -1 plus 1 over what? I. Clearly, right? And this is all squared. So this question has become complicated, and at this point, you just simply say that you have this expression. See, I have -I, right? plus 1 all over I squared. So I'll take, you know, when you have this expression, you just square top and square down, right? I'll have negative I plus 1 squared over I squared, as simple as that. The top one still remains 1 minus I squared over, here becomes negative 1. So as simple as that, this expression becomes negative of all squared. So this remains the answer, okay? After simplifying, we got negative of the expression 1 minus I squared. We can choose further to simplify this. So let's break it down, and we are going to get negative. Now let's simplify what you have here. 1 minus I all squared. This one is simplifiable, I'll see. So I'll have 1 squared and this. I'm trying to square it, okay? So I'll have, the negative should be out. I'm going to have into brackets, one bracket will have 1 minus I, another bracket will have 1 minus I, as simple as that. This gives negative of the expression 1 1 1. 1 times negative I, negative I times 1, negative I times negative I. Please take note of this. Negative I times negative I. Negative is positive. I times I is negative 1. So the answer is negative 1. Okay. So what do I get? My negative is still outside. I'll have 1 minus 1 to be 0. And this gives me what? Negative 2I. I multiply and I simply get what? Positive. I get positive 2I. As simple as that. So this is the finalized answer for the expression above here. So please, you can reverse the video and go through again and see how we solve this as simple as possible. Let's move to next question. Let's solve plenty questions as much as we can. So please, that's what I'm rushing through as fast. Question 4. Our fourth question says that if Z is equal to A minus IB, if Z is equal to A minus IB, then what is I cubed times Z? As simple as that. So if you have Z to be equal to A minus IB, what is I to the power 3 times Z? So what do you do? What is your I cube? Remember, I cube is equal to I times I squared, right? What do you get? I, this is what? Negative 1. So I'm going to get negative I, as simple as that. This remains, this is negative 1. You get negative I. So what we are asking us to find is, you are finding negative IZ indirectly, okay? So this is what you are doing. So what do I do? My Z is here. If I want negative IZ, I'll multiply negative I by this. So Z then becomes what? Negative, So I want to find negative I, and I have negative IZ, okay? So I'll simply multiply negative I by on both sides. So I have negative IZ is equal to negative I multiplying A minus IB. This gives me negative IZ is equal to, this gives me negative IA. Then now negative I again. The negative become positive. I become negative 1. Okay, that gives me negative B. So my negative IZ is equal to what? Negative B minus IA. Okay, the question asks us to find negative IZ. We want I cube, right? I cube. So, well, in a way, you can say that don't try to simplify this in a way, because the I cube that you have here is just the whole question given. If you try to divide through by negative, you end up deceiving yourself, because the I cube itself is what you have here. This one was just trying to simplify what you have to multiply. So this remains our answer. So meaning when they ask you to find I cube times Z, they just want you to multiply negative I by this side back, and you get your answer. As simple as that. Okay, so let's continue. So I'll have question 5. So question 5, I have now, we are moving to a deeper part, okay? So for the deeper part, it says write the expression square root of 5 multiplying ei tan inverse of 1 out of 2 in the form of a plus bi, okay? So write this in the form a plus bi. So how do you write this in that form? You just simplify this. Don't be scared by this expression square root of 5 tan. No, don't be scared. First of all, you move straight to the tan. This tan expression is not simplified. So I have square root of 5 e to the power I. What is tan inverse of half? Tan inverse of half. Just punch tan inverse of half. And that gives 25.56 degrees, okay? So this expression, which is tan inverse of half, will give me 26.56 degrees, okay? That is what you have here, please, like this. And you have been asked to express this in the form of what? A plus bi. Remember that in the linear form, r e to the power I theta is equal to cos theta plus I sine theta. As simple as that, where r is standing outside. So here, simple, I have my square root of 5 outside. I'll have cos of the angle 26.56 degrees plus I sine of the angle 26.56 degrees. And that is our answer. So please observe the kind of questions you should be expecting in the exams, okay? It's very simple but a little bit tricky. Let's move to the next question. So for the next question, that's question 6. So for question 6, we are going to solve an interesting problem. 1 plus I to the power 10,000. They say we should solve this expression. How do you simplify this? 1 plus I to the power 10,000. So we want 10,000 times of 1 plus I expression. That's crazy. But the Moivre's theorem made it very simple. This is an application of the Moivre's theorem, okay? So the Moivre's theorem said that if you have z, right, to the power n, right? So let's say, let me use the cosine. We are going to have cos theta plus I sine theta, okay? All to the power n. Then by the Moivre's theorem, instead of you multiplying this n times, you simply say cos n theta plus I sine n theta. And this is a very great formula we use to find complicated complex numbers problem. Yes, complicated complex. That's why you call it complex, right? So you're going to have 1 plus I. For you to apply the Moivre's theorem, you should have your complex number in the polar form. In the polar form, we see angles and we see magnitude. In this form, we are seeing numbers and imaginary. It will be difficult. So let's enter the polar form. 1 plus I in the polar form, what do? You need your r and you need your theta. As you're solving more problems, it's a way of you revising and knowing everything. R is modulus, which is equal to the square root of x squared plus y squared. This gives me 1 squared plus 1 squared because the coefficient of each is 1. And I'm going to have square root of what? 2, right? So meaning our r is square root of 2 is noted down. The next to do is to find our theta. What is our theta? Our theta is simply equal to tan inverse of what? The coefficient of our imaginary 1 over 1, or which we say tan inverse of y over what? X. Tan inverse of 1 is what? 45 degrees, right? So you punch it into the calculator. Tan inverse of 1, that should give us 45. So our theta is simply equal to 45 degrees. Now I'll just simplify this and I'll get square root of 2 e to the power I times 45 degrees. All this to the power 10,000. You see where we are now? Now we can apply the Moivre's theorem. What does the Moivre's theorem say? Just multiply this expression by this. Now if you have to multiply 10,000 by 45 degrees, bigger. So let's convert it from degrees to pi radians. So 45 degrees over 180. We'll convert this into pi radians. So 45 over 180, that gives 1 over 4. So this is 1 over 4 pi. Okay, so our expression then becomes square root of 2 multiplying e to the power I pi on 4 all to the power 10,000 should give us square root of 2 to the power 10,000 e to the power I pi on 4 to the power 10,000. So this is how you apply the Moivre's theorem. Okay, the Moivre's theorem simply says that the power should multiply our powers, as simple as that. The 10,000 multiply what we have as powers, so to take in the form of the square root of 2 on this side. So let's see the answer for this. Remember, this is to the power half, so 2 to the power half multiplying 10,000. Okay, multiplying e pi over 4 multiplying 10,000. Well, you have our I here. So here 2 can go into 10,000. I have 2 to the power 5,000. E to the power 4 can go into 125. So 250. Sorry, 2,500. Okay. So I have 2,500 pi I. And this is your answer. As simple as that. So if the OBJ or if the question demands you leave it in A plus BI, this simply becomes 2 to the power 5,000 outside the brackets 1,500 pi, okay, plus I sine 2500 pi, sorry, like that. And that is all you need for your answer. As simple as that. Take notes, go through again, solve it well. Let's move to the next question. As simple as that. So for our next problem, still on complex numbers, let's solve more interesting problems. Okay, you're gonna have this question. Let's solve our 7th question. We have z is equal to I to the power I. Let's solve a logarithmic problem. Solution: we've been asked to find I to the power I. How do we solve I to the power I? Now let's make use of the natural log. Okay, to find the value of I to the power I is very simple, but not that simple. Okay, so what do? First of all, z is equal to I to the power I. In order for you to solve any logarithmic problem, please take note of this. Make sure you remove the I and bring it down to simplify. How do I remove the I? I can remove the I by taking what? Natural log on both sides. That is the only way. Natural log on both sides. So natural log of z should be equal to natural log of what? I to the power I. Now in the logarithmic form, I can bring my I down by logarithmic rules, right? As simple as this. At this point, we can then convert this I attached to the length, and we convert it to the polar form and we move on. So length z is equal to I multiplying the expression length of I. What is I? On the algebra diagram, we have our imaginary I on top, our real part, which is positive, negative, then negative imaginary. You realize that the magnitude of I is 1 and the angle from the positive axis is 90, so it's pi on 2. Okay, so you have e to the power I multiplying pi on 2 plus 2 pi k. Okay, take note of this. Your argument is pi on 2 plus 2 pi k. Please, 2 pi k is an extended argument. It tells the different revolution that will affect the answer by the same thing. Okay, you can choose to ignore, but you can still add it. Okay, so pi on 2 depends on the nature of the answers. So at this point, when you have something like this, close brackets, length z is equal to I multiplying this expression. Once you have this expression, you realize that length e gives you 1, but you bring this down. So I have I multiplying pi on 2 plus 2 pi k multiplying length e. Please go and revise your indices